Good morning, everyone. First of all, I would like to thank you all for being here today. Today is online webinar on bio-based nano-additives in polymer composites. And once again, I would like to thank you all, and especially our presenters who are going to be here and talk about the subject. And without further ado, I would like to introduce our first speaker, who is Professor Dimitrios Bikiaris. Professor Dimitrios Bikiaris is a professor at the Department of Chemistry at the Aristotle University of Thessaloniki, with a special interest in the science and technology of polymers. His scientific work has been published in more than 560 scientific papers in international scientific journals, has more than 26,000 references, and an H index of 85 according to SURPASS database. He is also the coordinator of the REDONDO project, and the professor today will introduce us into the REDONDO EU-funded project, its goals and impact. Professor Dimitrios Bikiaris, the floor is yours.
Thank you very much, Kostas, for your kind introduction. I would like to thank all the participants to this workshop. And I will start with saying a few activities about the presentation of the work of REDONDO in this workshop and what we're doing. Just to share my presentation. Okay, do you see the presentation?
Yes, we can see it.
Okay,
Excellent.
In the presentation mode, Kostas.
Yes, it's fine. Yeah, we can see it in full screen.
Okay, then we can start. REDONDO project is a project that has to do with cross-linked polyethylene pipes and cables. And we try to do the thermosettings as reversible materials because it is a big problem with all this, and I explain why. Just a word about the life of the plastics. We know all that the production starts with some raw materials, monomers, taken from virgin feedstock. Mainly, all of these are coming from oil. We're using these monomers for the conversion of plastics, and then the second stage we produce several products, bottle, films, cables, pipes, etc. Then we have the consumption of these all products, which means we have the life of these materials, and this can take some years. For example, pipes should be stable for 70 years, and some other films for food packaging application are usually only for a few seconds or minutes. Then we have the big problem of waste of all these materials. We need the waste collection, and we are using some of them for energy recovery, energy production. But the most, as we will see, of these are ended to landfill, and here they cause a lot of problems. So we need to collect all of them and separate the different kinds. We have too many kinds of polymers, some millions, I can say, and to separate and to use again, to recycle them and to reuse. And here we have two big problems with the production of polymers. Till today, it is estimated that 9.1 billion tons of plastic have been produced since 1950. We started there the industrial production of polymers. About 350 to 400 million tons of plastic are produced every year. And as we can see, we started from 2 million tons in 1950 to 400 tons in 2017. And you can see that polymers are everywhere, but the most of them are in packaging materials, about 40%. And here they cause a big problem because it's very difficult to be recycled because all of these are too light. And we have two concerns here, two problems we must solve. The first is the carbon dioxide emission for each 1 kilo, for example, for polystyrene or PET, 2.4 kilograms carbon dioxide are emitted in the environment. And the second big problem is the microplastic pollution, because the 70% and or higher amounts of all these produced polymers are in the landfill, and they decompose slowly due to UV radiation and mechanical cleavage, and microplastics are produced. This is the biggest problem of the last years. So where are we today about the plastic life? Only the 10% is recycled so far. Europe is the leader in this activity. 20 till 20-30% of all used plastics are already recycled every year, but the amount is too small. Another amount, about 12%, is incinerated for power generation, for electricity, the most part of them, but the biggest percent of the produced plastics, 78-79%, is discarded and accumulating in the environment, oceans, lakes, rivers, and landfills, causing the biggest problem of microplastics. And the trend is the next years to increase the recyclability or to increase the incineration of all of these produced plastics and to reduce the disposal, the discard in the landfills. But all polymers cannot be recycled. For example, can be recycled thermoplastics, but not thermosetics, as in the case of cross-linked polyethylene that deals with our REDONDO. REDONDO is a new project with a consortium of 11 partners, about 4.651 million euros. And we started about 1.5 years ago 2 years ago, very close, in September, 1st of September in 2020. And Aristotle University is the coordinator of this project. CNRS from France, from Montpellier, is the other institution that participates in this project. We have also a lot of SMEs, big companies, Creative Nano, Itene. Ceylon is the producer of cross-link material for pipes and cables. And these are produced, the pipes from Interplast, an SMEs company here in Greece. And KBA produces cables in Berlin. We have also Amen, ISQ, Axia, and RDC in this project with several activities, life cycle assessment, dissemination activities, and other. What is the main aim of this, the main challenge? To make cross-linked polyethylene reversible, because polyethylene is the most widely used polymer for several applications, plastic parts, bottles, and exhibiting a range of properties depending on its density, because we have different kinds of polyethylene here, low density, high density, ultra high molecular weight, and etc. But for several applications here, these thermoplastics are not appropriate. So we're going to cross-link polyethylene, especially high density polyethylene. You can see here the cross-linked materials with completely different. There are two different methods. Peroxide is the first one. Some radicals are created between macromolecular chains, and they are joining together to produce cross-linked materials. And the other method is to use some silanoate compounds, like in this case. The problem in both methods are that all of these are very stable bonds, and it's very difficult to be breaking down. We need these cross-linked materials. Will increase the next, let's say, the next years, the production of this. You can see here the estimation till 2028. But the problem, as I said, is that they are not thermoplastic materials, they are thermosetics. And most of them are using in cables and pipes, 44%, medical fields, automotive industry, and others. The drawback, we have very good properties. They are stable in high temperatures, especially for hot water that is going through pipes, but they have many drawbacks. Is a thermosetting material cannot be remelted and to be recycled as thermoplastics, and it's a very big problem where we can use all these materials. In the case of Redondo, we try to solve this by producing thermosettings with the reversible cross-linked bonds. Our task here in Aristotle University is to produce some sulfur, disulfur reversible bonds, and Montpellier CNRS to produce such bonds. I will present some example lately with DSL reactions. And also, we must increase the other properties of all these materials by using green bio-based additives like nanolignin, nanocellulose, modified. Creative Nano will give some examples, and all this material will be for the final application, pipes and cables. And our aim is to produce these reversible cross-linked materials and to see the recyclability of all this. There are several work packages that are communicate between them and interacted, starting from the synthesis of polyethylene, cross-linked PEX, using the additives, producing the final materials, life cycle assessment, sustainability by design of all these material tests, and for sure safety of these materials. In our system, the reverse cross-linked carbon sulfur disulfur bonds are based to two different approaches, to different methods. The first one is to use carbo-dithio bonds, and the second carbo disulfide bonds. The aim is all these materials to be stable at temperature 130 to 150 degrees Celsius required for pipes, and after to be remelted to break down all these bonds at temperature higher to 150 to 170 and to produce the reverse materials. All this can be easily produced, starting with our initiators, peroxide initiator, tetramethyl disulfide, in order to produce all these bonds. The peroxide will break it down to produce a radical. This will be connected with macromolecular chains of polyethylene, and then the sulfide bond will be produced. And as we have seen from our previous test cases, all of these can be reversible materials. I will not say too much about this. And Montpellier will use Diels-Alder reactions in order to produce this reversible bond, starting from formaldehyde, in order to produce this compounds, these bonds. And this also would be stable at low temperature, and at higher temperature will be cleavage. And there are too many applications and too many published papers in this field, and we have already very good results. This will be the intermediate bond for the cross-linking pipes, which will be for cables breaking down in higher temperature. And we have, as I said, also additives, nanolignin, nanocellulose, tannins to enhance the antioxidant properties, flame retardants, and other properties of the final materials. Of course, several studies in safe and sustainability by design for all the used material, the toxicity, and concerning this workshop, except Redondo, some results will be presented from Redondo, from our partners, and there is a participation of this project, ESTELLA, REPURPOSE, and SURPASS. And okay, I will pass very quickly. We have all the agenda. We will start with cellulose derivatives composite production. Pilar will present it from Itene. Thereafter, we have the ESTELLA project, corporation of lignin from Creative Nano, Hymen, and we will finish at the end by Alexandra Zaboulis present some activities. The website, if you want to see more about the project information, you can visit the website and to find everything there. I think I was on time. Thank you very much for
Thank you so much, Professor, for a very informative presentation.